Let's find this element quickly. Hello everyone. So in today's tutorial, we have this sorted array, right? So this array has 11 elements, this is their indices, and these in the blue are the actual elements. So 1, 2, 5, 6, 9, 10, 11, 14, 16, 17, 20, 24, right? The first thing I want to mention is to make sure about is this is a sorted array. They are in this increasing order. So now, given we have a task that we want to look for one of these elements, let's say 16, okay, for the purpose of this tutorial. What we can do, and the obvious way to look for this, is like if you have a big phone book and you are looking for a number and you are going from 1 to 1, right, until you find what you are looking for. So you start an iterator here and then you check, is this 16? No. Is this 16? No. Is this 16? No. All the way until you get here. This takes n length or O of n time, because this depends on the length of this array. If this is 1 million or 1 billion or 1 trillion elements, you are going to loop through all of them in the hope to find what you are looking for. In case you don't find it, you are going to iterate through all of them. In case you do find it, it depends where you find it, but there is a better way. So this is called a binary search, and it's not an efficient way of doing this. So a binary search is where you will start by cutting, like going to the middle of this array, comparing whether what you found is bigger, or like greater or smaller than the value you are looking for. So in order for you to do that, you have to find the middle, or like the average of the array. So you need a first iterator here, let's call it low, and a second one that is here, let's call it high, okay? And then we need one in the middle, let's call it mid. So it's somewhere here. To find it, what we can do is to take the greater element and then add it to the smaller one and divide it by 2, right? So in this case, 5 and the remainder is 1. We don't care about it. This is the middle, right? So mid. The problem with this approach, though, is that when you try to do an addition for these two elements, the biggest, or like the greatest, the highest, and the lowest, what you might come to is that you are adding two integers that might overflow. Means, let's say they are 8-bit integers, so it means that you get, let's say this one is element number 120, and let's say because the low will keep moving, let's say the low moves to 20, so this means that this is 140. There is no 140 in 8-bit integers, so this would overflow to minus 116, and that's a big problem. To avoid that, there is you can change this to extract it to its own function, check whether you are overflowing or not, which is like a valid option, but the most obvious one, that is this one. So you take the the low plus the high minus the low divided by 2. So the low plus high minus low divided by 2. So you subtract the low from the high, the result you find you divided by 2, and then you add it to the low. And so this and this will give, so this one will be low plus high divided by 2. So while those ones give the same result, they are different in that this one protects you against integer overflows, okay? And this is the right way to do this. So for our first mid, it's at 5. So now we have the mid. Now we compare, does this equal the value we are looking for, which is 16 or 17? Okay, let's keep working with 16. Okay, so does this equal 16? No. Is it greater or smaller than 16? It's smaller, right? So what we do, we take the low and we move it here. Low, okay? By which we are doing basically this. We are getting rid of all these elements and we are working with this one. So mention here that the low is one step, like one element in front of the mid, okay? With the high, we will not do that. We instead include the high. It's not exclusive because we need to include one of them and exclude the other one. If we exclude both of them, we might run to an issue where we are avoiding a number, you know what I mean? So that's one thing also to keep in mind. So let's continue. Now we need the middle of this. So the middle of this is that we take 6 plus 11 minus 6 divided by 2, right? So 11 minus 6 is 5. 5 divided by 2 is 2. The remainder is 1 plus 6. So 8. Now, this is the element we were looking for. That's the mid. We compare this with whether that's the number we were looking for. It is it. So we are done. So we just calculated the mid once, then twice. We get to the value. If let's say it was I don't know, let's say it was 14. If it was 14, when we find the mid, we compare it. Is this the value what we were looking for? No. Bigger or smaller? It's bigger. So what we do, we take the high and we move it here, like I said, in the same position of the mid. So we do this and we make this the high. Sorry, we make this the high. Okay, so now we calculate again the mid. We are going to find it somewhere here, and that's it. We will just do the same calculation and we will find it. Now let's see this in code. As we can see, here we have the same array 1, 2, 5, 6, 9, 10, and so on. And given we are going to try our first way, which is the linear search, which takes O of n time. And because they both take the same space, by the way, because what we are doing nothing except looking through an array. We are not creating any new array or new hash table or any other thing. So now to do that, what we need to is, given we have the high stack, so the array, what we do for, let's ignore the index by using this blank identifier and range through high stack. And here are the results. So if needle, the element coming from here, equals the value that we get from the array, return true. Otherwise, we return false. Okay. So given it was 16 as our first value, run true. And let's say we give it something else, like, I don't know, like 200. And we know we don't have 200. It means that we did loop through all of them. To check that, fmt.println, okay, and v, you will see all them here. You see all the elements. That is a wrong way of doing this. Now, let's stop doing this. Let's comment this one, the linear search. Let's uncomment the binary search. So func binary search, we are basically going to do the same thing. So we return a true or false. Okay. So we need to find the low, right? Equals 0. It's the first element of the array anyways. The high equals the length of the high stack. So the high is, we calculate the length of the array. For low smaller than high, we do our checking here. The first thing is we calculate the middle, right? So the mid equals the high, the low, plus, we open the parentheses, the high minus the low, those again in parentheses, divided by 2. So that's the mid. Now, let's say value, high stack, and then mid. Mid, like I said, the index, and now we are getting the value. So we have 3 possible statements. It can be bigger than what we are looking for. It can be smaller, or it can be it. So let's start with our happy path. If needle equals value, return true. Else if needle is smaller than value, and else if needle is greater than value. Okay, so these are the possible elements, the possible cases. Now we are going to return false, because if we get by there, so it means we didn't find anything. So what if the needle is greater than the value? I think it makes more sense to compare the value with the needle, not the needle with the value. So I will switch this here, and then needle. So we are comparing the value we are finding here, right? That's what we are comparing. So if it's smaller than the needle, then the low now equals the mid plus 1. You did see here when it was not it, what we did, we started from here, so plus 1, right? Now for the high, we just, like this one, or it was this one, so we did include it, so this one is inclusive, right? So let's run this. Okay, we forget a parenthesis here, not a big deal. True. Oh, okay. 200 is returning true. It should return false. Okay. We are providing it 909. I'm sorry. Okay. False, because it doesn't exist. If let's say it's 20, and we know it does exist, it's true. Let's do something. fmt.println value, just to see what we are doing. See, we are checking for values before we found it. If we check with, let's say, 9, for like 4 times. Let's say 10, 3 times, you see? It's way, way better than just linear search where it takes O of n time, like the upper bound. So thanks for watching. I will leave another 2 links who explain from a Google expert about this, the middle, like this one, and how it's a mistake if you do the other way. And the other thing is, there is a project like a rocket launching that did fail because of an integer overflow. I will also leave a link to that in case you wanna look that up. Thanks for watching, and see you on the next tutorial.